This example has a kind of a funny looking graph here. And then it asks us three questions. It says, where's the limit defined? Where's the function continuous? And where's the function differentiable? Well, first off, what does it mean for limit to be defined? Do you remember that? Let me remind you when it's not defined. So say you have a function that from the left side it comes up and hits an open dot there, and from the right side it does whatever. Then right at this point, it's the I should say the limit does not exist. It's got to be the same from the right and left. So for a limit to be defined, it must be the same on the left side and the right side. You can't be at different heights on the left and the right of a point. So that never happens here though, right? It's just, there's none of this kind of there's none of this kind of stuff going on. So it's everywhere from -10. This, you can see the graph there. It goes from -10 to +10. Everywhere from -10 to +10, the function is defined. I'm sorry, the limit is defined. The limit is defined. Now you might say, yeah, but what about right here where there's a hole? There's a hole in the graph. That's okay. It's still coming to the same height from the left and the right. Right? The left side's coming up to three. The right side's coming. You might say, yeah, but it doesn't actually hit three. Remember, we don't care about that for limits. Now we're going to care about that for continuous. We'll get to that. That'll matter for continuity in a minute, but it doesn't matter for limits. Remember, limits don't care where you end up, just what you get infinitesimally close to. Is that concept sinking deep for you? You got to really get that down straight. A limit is not where you end up, but where you're headed. A limit is not where you end up, but where you're headed. We don't care whether it could be a solid dot here, it could be an open dot, whatever. We don't care. It's headed from the left side to a height of three, and it's headed from the right side to a height of three. From both sides, it's headed to the same height, even though it never actually arrives at that point. We don't care. It gets infinitesimally close to a height of three from the left side and the right side. So the limits from the left and the right are both the same. So it has a limit defined at that point, as well as all the other points. So everywhere from -10 to +10. You might say, what about, why don't we put a bracket on these guys? Well, they specifically told us down here, each interval don't include the endpoints. So again, you remember that parentheses do not include and brackets do. So we put parentheses there. We'll talk more about that down here and continue. Let's talk about continuous. So the function is not continuous right here. So right there, it's certainly not continuous, even though the limit exists and is defined. It's not continuous. Continuous means you don't pick up your pen. So if you're drawing this graph, right there, I got to pick up my pen to keep drawing. I can't draw through that point because it doesn't exist there. So that's not continuous right there at zero. Well, that's why they put the answer like they did. See, they didn't just say, you might say, isn't that the same as just, how's this different than just saying -10 to 10? Well, if they said -10 to 10, that would include zero, and they are specifically not including zero, not included by the way they wrote their interval. You see, because zero's not in that interval and zero's not in that interval, right? Remember, parentheses don't include. If you write like -10, 0, and you put brackets, that includes, oops, that includes 0 and -10. That includes the two endpoints. If you put brackets have a straight edge to them, you're straight on those numbers. But parentheses are rounded, which means you're around the number, but you're not right on it. So like you're close to zero, but you're not right on zero. You might be, oh, right here, you're close to zero and you're close to 10. You might be close to zero, like you might be 0.0000001, but you're not straight on zero. You're just close to it. So zero is not included, which is right. Zero is not included because right here at x equals zero, the function is not continuous. And then the final one, differentiable. What does differentiable mean? That means smooth. I know that's probably a new concept for you. It's a preview of coming attractions in chapter 3. We're going to be taking derivatives. So it's getting us ready for that. it's helping us to see it on a graph first off. So a function is differentiable if it's smooth. By smooth, I mean smooth, not jagged. So for example, let me give you another example of a graph. If you had a graph, say, and you had a function on that graph that was just smoothing along and chirp, oh, well, that'll be fine. And then we're like that. See how it's jagged right there? So right there, we would say, right at that point, it's not smooth. It's not differentiable right at that point. It does a little jag. So it's like these are like increasing levels of niceness. First off, is it same left and right? That's limit defined. Is it continuous? You don't pick up your pen. And then is it not only continuous but smooth? We don't like jags. Well, it's going to be the same answer as continuous because right at zero, right here in the middle, it doesn't even exist. So that's certainly a jag, right? It's not. You might say, well, it kind of looks with yeah, but it doesn't even hit there. You have to stop your pen and come down here. That's a jagged move. That's not a smooth move. You have to be connected at least to be smooth. It's not even connected at zero. So it's not smooth there. So same answer, not including zero. And so there we go.